we start with an achiral substrate, starting material, and the reagent it reacts with is also achiral, only an optically inactive product will be formed. This achiral alkene reacts with hydrobromic acid to generate an achiral alkyl carbocation intermediate. This then interacts with an achiral bromide that can come from either behind the plane to give one alkyl bromide, or alternatively attack from in front of the plane to provide the other enantiomer. Because both the substrate and reagent are achiral, the resulting enantiomers are in a 50-50 racemic mixture that is optically inactive and can be depicted by a plus and a minus together. What happens if we go from a substrate being achiral to having a stereogenic center? Now it's chiral, and the two enantiomers of this stereogenic center react at the same rate to form an alkyl carbocation. The rear and front of this intermediate, as shown here, are not equal, so the approach of the reagent from the back or the front face is also not equal. Thus, the bromide reacts with the carbocation to provide an unequal abundance of diastereomers. Where the substrate is a 50-50 racemic mixture of enantiomers, it is chiral but optically inactive. The product is a 50-50 mixture of enantiomers that is optically inactive, but not a 50-50 mixture of diastereomers. Where the substrate has enantiomers not in a 50-50 ratio, so non-racemic, thus it is optically active, the product is not a 50-50 mixture of enantiomers, nor diastereomers for that matter, and it's optically active. But if we start with a single enantiomer, thus a single stereoisomer, the product that ensues isn't a single stereoisomer, despite being optically active.
It's important to notice here that there is a slightly different way that bonds are drawn. We've been used to wedges to our bold and hashed lines. This shows absolute stereochemistry. However, a slightly different bond that's misused by some has an equal width to the bond. This indicates relative stereochemistry. It depicts the two possible enantiomers that have that relative spatial relationship shown. We will go back to the three scenarios that we briefly discussed and look at them in more detail. First, where the substrate has a 50-50 ratio of enantiomers. Thus, it's racemic and optically inactive. So, from our starting material with a 50-50 ratio, we form the intermediate still with a 50-50 ratio. All this assumes that the reaction conditions don't alter the original stereogenic center. Now, we know that the front and back faces are different. Thus, we derive the four products with the resulting 4:1 diastereoselectivity to give a ratio of the four products of 40 to 10 to 10 to 40. We shall identify enantiomeric pairs in the products. And you can see that each of the two pairs have an equal amount of each enantiomer. So, we have a 50-50 mixture of enantiomers, making all the products together optically inactive. However, there isn't a 50-50 mixture of diastereomers. In the next scenario, there is not a 50-50 ratio of enantiomers. So, overall, the substrate is non-racemic, so optically active. To be more specific, if there is a 90-10 ratio of the enantiomers, this will carry through to the intermediate, and the four products generated with a 4:1 diastereoselectivity will provide a ratio of 2 to 8 to 18 to 72. There are still two sets of enantiomers, but neither has a 50-50 ratio of enantiomers. So overall, the products are optically active. Lastly, when we commence with a single stereoisomer, so the ratio of enantiomers is 100 to 0, this is again carried through to the intermediate, and with the products being formed in a 4:1 diastereoselectivity, we get a ratio of 0 to 0 to 20 to 80. When we look for a pair of enantiomers, we find none present, but we no longer have a single stereoisomer, and the product overall is optically active.